Now let's move forward for give you a short summary for instantaneous reaction. So in order to confirm whether the general rate equation we derived from previous class can be performed in instantaneous reaction, no matter it's at low CB or high CB cases. So let's give you a quick review. So for instantaneous reaction, because the reaction in liquid film is very fast, so A is not have chance to enter the bulk liquid. So the molecule A will completely consume in at the reaction plane in instantaneous reaction. So based on this, we can directly drop the reaction resistance. And at low CB case, as we know, we assume the transport resistance in gas film is very fast. Transport is very fast and resistance is very small. So you can delete this term out. So the rate equation in instantaneous reaction at low CB cases will express like this, is identical, and the E here you need to use the EI. It's a maximum value for E, right? And at high CB cases, as we know, also there's no chemical reaction happen in bulk liquid, and because the reaction plane already be pushed to the interface between gas and liquid, so A don't have chance to enter the liquid film, right? So we don't have a liquid film resistance. The only resistance we have here is the transport resistance in the gas film. So you also can completely write down the rate equation and only need to consider transport resistance in gas film. And when you slow the reaction to fast reaction in liquid film, then instead of the reaction plane we have in instantaneous reaction, here what we have is a reaction zone. But for fast reaction, all reaction only happen in the liquid film, right? So you also can directly drop the reaction resistance in bulk liquid. And so now you only have two resistance. The first one is transport in the gas film, and the other one is transport and reaction in liquid film. So as long as we know the E for this case, then we can complete this rate equation, right? So for low CB cases, we need to check the plot of E versus MH, that plot, then we can read out the E for at low CB case. And for high CB case, due to the B, we only spend tiny amount of B to react with A, so the concentration CB remain constant in the liquid film layer. So based on this, you can lump the CB with K, become a K prime. And here you can know that the rate constant becomes proportion to the CA, the reaction order becomes to 1. In this case, we call it a pseudo first order reaction respect to with A. And under this situation, the E, you can directly use MH to substitute E, then you can complete the IA 4 prime. Okay? And how can we get E at the low CB case in fast reaction? You need to check the plot I just we show you in previous slide is the E versus MH, this plot. And the horizontal axis is MH. As you know, when you increase MH means what? The reaction rate increase in the liquid film. So you can observe that the fast than instantaneous reaction. Okay, so how to read out the E for fast second order reaction? So first of all, as we mentioned, you need to calculate the EI for your experiments. as long as you determine what chemical equation you deal with and also the concentration of all reactants and also the working temperature, then you can calculate the EI by input all the information here. If the EI equals to 2, then all the behavior, all the E in your experiments will obey these curves based on different values for MH. So with increasing MH, you can see that your E will increase and reach the maxima EI and remain or maintain at EI here. So as long as you determine the value for EI, then next you need to calculate the MH. Then if your MH is equals to 4 here, then you read out the E here, then you can complete the rate equation. But if your MH is equals to 100, then in this case you know your E equals to EI, so it belongs to instantaneous reaction. Okay, and the green one actually is we mentioned is the pseudo first. For that case, based on these simulation results, you know E equals to MH. So that's why for pseudo first reaction, we use MH to substitute E and can help you to write down the rate equation or determine the rate equation. Okay? Okay, so let's move forward. How about if we lower the rate equation to intermediate reaction rate? And under this situation, you can know because we slow down the rate equation, so the reaction will occur in the liquid film and bulk liquid, no matter at low CB or high CB cases. So at this situation, you know what? Definitely how to formulate the rate equation. You will directly use the 4 general results, right? Then as long as you know the E, then you input all the information, then you can get the RA formula. So how to read out the E? For intermediate rate equation, you can use the simulation results, use this term, 1 plus MH squared divided by 3 to deal with the intermediate rate equation 1. Then you can get the rate equation. And how about we further slow down our reaction to slow reaction rate? For slow reaction rate, the characteristic of here is the reaction only happens in bulk liquid. So also we know there's no chemical reaction happen in liquid film. So E equals to 1, right? For both cases. And the difference between these cases is what? Do we need to consider the transport coefficient in film layer or not? For this case, we need to consider the transport resistance in gas film and liquid film, so you can observe the concentration drop as a function of location in the film layer. But in this case, transport is very fast compared to reaction, so you don't need to consider the resistance in film layer. So that's the only difference. So for the reaction, to a left-handed side, the case you need to consider the transport resistance. This is a solutions for that one. And for if the transport is very fast, the only thing you need to consider is the reaction rate. Okay, so this is reaction rate you need to consider. You don't drop this term out and only term you have is this one. Okay, and for both this case, don't forget because all reaction only happens in bulk liquid, so E equals to 1. Okay, you don't need to consider that. Okay, so this is a summary for intermediate and slow reaction. And for intermediate, no matter it's low CB or high CB, you just complete the rate equation we derive here, and you need to get the E, okay, here. And for slow reaction, determine whether you need to consider the mass transport or not. Then you also can complete the rate equation. Okay, so this slide actually is some definition for EI and MH. We already explained this, but we want to give you some supplementary information for MH. If MH is very, very large, larger than 1, that means what? That means the reaction rate is very fast than transport rate in the film layer. So all reactions happens in the film layer. So if I try to increase the volume of film layer, then they can speed up your reaction rate, right? So agitation is very important because agitation can help you to generate more bubbles, and more bubbles, you will have more volumes of film layer, so that will speed up your reaction. But if your case is MH, after calculation, MH is very small, smaller than 1, then they tell you what? The reaction in the film layer is very slow compared to mass transport. So reaction majorly happens in bulk liquid. So under this situation, even you generate more bubbles, that doesn't have no benefit to your reaction rate. Okay? Okay, so I'm going to give you a summary here. For fluid-fluid chemical reaction, you need to write down the transport resistance and reaction resistance, and the relative RT and RR is very important because you can determine which step is a limited step. Okay, and you also can identify the reaction location is in the film layer, or in the film layer, or in the bulk liquid, or in both regions. And we use this general rate equation can deal with all kind of situation we have, including that 8 different types of cases, right? And based on this, we also show you how to get the E in different cases. So you need to check the plot of E versus MH, okay? To determine the E, especially in the fast reaction and intermediate reactions. Because for instantaneous one, E equals to EI. And the fast, pseudo-fast, E equals to MH. You don't need to, as long as you got MH, you can get the E. And intermediate, you also need to check the E, right? And for slow, you don't need to check the E because for slow reactions, all chemical reaction happens in bulk liquid. So E equals to 1, okay? Okay, so let's give some examples here. If we consider reactions is gas A react with liquid B and we generate product R, and this belongs to instantaneous reaction because the figure I provided to you is a typical instantaneous reaction. You can observe the reaction plane located inside the liquid film. So the first question A, please formulate the distance of the reaction plane from the gas-liquid interface. Gas-liquid interface is here, so the question is asking you the reaction plane, the distance between the reaction plane and the interface. So what's the X? For instantaneous reaction, you can easily write down the equation by what? By flux, right? Because it's A moles A react with 1 moles of B, so when you write down JA should be equals to A times B, JB, right, in the liquid film. So based on this, you just formulate what's the JA? It's a flux concentration gradient, diffusivity concentration gradient, and times A, the diffusivity concentration gradient, CB minus 0. Gradient here is X0 minus X, you got this thickness. So you can simply get the X, okay? And some people probably will ask how to determine whether the CB is high enough to push the reaction plane to the interface, gas-liquid interface. How to determine the minima CB? So yes, the idea is also based on the equation of flux. The JA equals to AJB in the liquid film. And as you know, the JA, for this you use the transport coefficient, Kg Pa minus 0. And the JB will be obey the A times diffusivity concentration gradient. So based on this, you can get the CB. You know the minima CB, okay? So this is the cases for instantaneous reaction. And the second example I want to show you is the typical situation you will encounter in your experiments. you need to deal in your experiments is we have a no chemical equation is a gas A reacted with B, liquid B, then we generate the product R, and also we know the rate equation is a second order reaction, and we have a bunch of lots of information related to the chemical equation, and also have we know the concentration of reactants A and B. Can you write down the overall rate equation? Can you write down? Can you calculate how to do that? Because we know the chemical equation, we know the concentration of reactants and working temperature, so you know the rate constant and other parameters also. So first thing, to determine what kind of what's the rate reaction rate in film layer, you need to calculate the EI and MH. Based on definition, you just put in all the information here, and you get the EI equals to 5, MH equals to 15. So based on the figure, I just show you. As long as you have EI and MH, based on this criteria, you know what's the rate, what is the reaction rate. The reaction rate belongs to what? So based on this case, we know, MH is larger than 5 times EI. So we know MH is very large, right? So in this case, we know it is instantaneous reaction. Instantaneous reaction. And the second question will be, hope you can calculate the transport reaction resistance for each transport process or steps and find out which is the rate limited step. So after simply calculate the resistance in gas phase, liquid phase, and reactions, we find that the resistance in gas phase is a rate limited step because it equals to 1000, is much larger than resistance in liquid phase and reactions. And finally, you can, as long as you know this one, you can get the overall rate equation by what? Use the PA to divide it by total resistance. You just sum this up, then you can get a roughly consumption rate or overall rate equation for these experiments. So this is how we usually deal with our experiments. And following, probably you have the other examples, but this is not it's a special cases. Why? Because what we have here is we have gas A bubbling through a tank of aqueous B. And reaction, equation we have is a gas A react with 2B, generate R, and we know the rate equation, it turns out is a third order reaction. And also with lots of information about this experiments. Why? We have a third order reaction, but Professor, it's very difficult to us because as our assumption in the beginning of fluid reaction, we assume all reaction we deal with is second order. Yes, you only can deal with a second order reaction. But now you have a third order. How to do that? Yes, here. This is a special case, I tell you. So because you only know how to solve the second order reaction, so what we can do here is we assume it is a second order approximation. We assign probably it belongs to second order approximation. So here what we deal with is KCACB prong, right? So we move one CB lump with K, and this is a new rate constant, and allow it to become a second order reaction. So next is the same idea. You need to calculate the MH and EI and compare the magnitude of EI and MH to find out which reaction, chemical reaction What's the reaction rate? So one thing you need to remind you is the based on definition K here actually is a K, right? But now you convert it to this one, so this is a K prong, so you need to use this K prong to substitute this K, so you will get the KCB prong, or say KCB square. And after calculate, you got the 100, but when you input all the information here, I just remind you, I hope you can input the unit here. So MH actually do have a unit, so you need to have a unit when you write down your answer sheet. Okay, EI, the same thing, you need to input all the information. And one thing I want to remind you is, actually the information given to you is we don't have a PAI. What's a PAI? PAI is the partial pressure of reactant A at the interface between the gas and liquid. We don't give any information about the PAI, but here you can use the PA to substitute PAI. Because what? You can because I can explain why. But at least we guess PA equals to PAI, then you got the 1000, right? So you find that, okay, compare the magnitude of MH and EI, you find EI is larger, it's much larger than 5 times MH. So it belongs to pseudo first. So let's check back. If PAI usually is equal or smaller than PA. If it is smaller than PA, then the value for EI will larger than 1000, and it's still larger than 5 times MH. So the final decision, final results doesn't change, right? Because EI is still much larger than 5 MH, so it still belongs to pseudo first. Due to it belongs to pseudo first, so E here will be, you can directly use MH to substitute here, so you can easily get out the consumption of reactant A per reaction volume here. And don't forget, you need to put a unit along with your answers. Okay, so today we just ended here.